All right, guys. So part two of your final review. I want to start off by talking about sequences and series. So we've got two different sequences and series we want to look at. Arithmetic is defined by a common difference. Common difference. And that's when we're increasing or decreasing at a constant rate. We've also got, we can find the nth term in a particular arithmetic sequence by taking the first term and adding n minus 1 differences. So think about what that means. A quick example. If our common difference is 3 and our first term is 15, then we can find, let's say, like the ninth term, for instance, by taking our first term and adding, in this case, n minus 1 would be 8, so 8 common differences. And we can find the ninth term in terms of just by knowing the common difference in the first term. Summation notation for this particular thing, we're looking at, this is our sigma notation, so from k equal 1 to n, so we're going to add n terms together. This is the notation, the first term plus the common difference times k minus 1. So that's what the sigma notation for this particular thing would look like. If we go over to geometric sequences and series, we've got a common ratio. So in this case, it's not increasing or decreasing by the same amount every time. It's actually being multiplied. By something every single time. And we looked at different scenarios. Traditionally, our geometric sequences are going to be when our common ratio is less, the absolute value of our common ratio is less than 1. So we've got a ratio that is, less than 1 and greater than 0, so in between those two values there. So this, we can find the nth term with geometric. We can find the nth term by taking the first term and multiplying n minus 1 common ratios together. So again, as an example, we want to find the ninth term, and we know that a sub 1 is equal to 12, and our common ratio is 1/3. We can find a sub 9 by multiplying 12 by 1/3 to the 8th. And you can figure out that on your own. So the biggest thing with this is, last thing, we've got the summation formula here, or the sigma notation. So we're going to go from k equal 1 to n on a geometric sequence here, or I'm sorry, series. And this is important that you understand that this is a1 times r to the k minus 1. It's always k minus 1. So just as an example, a quick example, we need to make sure that if we're going to go find the sum of this thing, that and this is in the form of the sum of from k equal 1 to n, a1 times r to the k. We need to change that into this form. And so our a1, or our constant that we need to use here, we would actually pull an r out of there. So we would go a1 times r to the k minus 1 in order to get it into that form. So this would end up being the sum from k equal 1 to n. We're going to pull this constant out in front, a1 times r of r to the k minus 1. So just a reminder, make sure that it's in this form if we're going to find the sum of that particular thing, of that geometric series. Okay, next thing we want to talk about are summation formulas and different forms of summation formulas. We've already given you the sigma notation up here. So how we can find the sum of, let me switch back to the other color here, the sum of an arithmetic, of the first n terms in an arithmetic. This is the notation, S sub n. And the sum of the first n terms is equal to the average of the first and the last. And we're going to multiply that by n. And there's a proof that goes along with this. That proof essentially looks like this. So let the sum of the first n terms of this thing equal S sub n. So we're going to represent it as S sub n. There are two different ways that we can write S sub n. We can write it from the beginning. So S sub n equals 1 plus 2 plus 3 all the way up to the second to last term and the last term. And then we can also write it in reverse order. So S sub n is equal to, here's the last term, second to last, third to last, and so on. And so what happens is when we combine these, so we're just going to use, we now have a system of equations for S sub n, and we combine those two. We have n plus 1s when we combine these two. So here's an n plus 1, here's an n plus 1, here's an n plus 1, so we just pair these things up. We have n of those, so 2 times the sum of the first n terms, and this arithmetic sequence is equal to n times n plus 1. Divide by 2, and we've got our summation formula. So that would be the proof. Obviously, you want a let statement and a conclusion. You should be able to do that for the final. For geometric, we've got two different summation formulas. So the first one is the sum of the first n terms in a geometric, and that sum is equal to the first term times 1 minus r to the n over 1 minus r. So this will give you the sum of the first n terms in a geometric. This is not very solid technical notation, but I think it gets the job done. The sum of all of the terms, or the infinite sum, of a geometric is equal to a1 over 1 minus r. And that's because as n approaches infinity, r to the n becomes 0, leaving just a 1 in the numerator. So it simplifies to a times 1, or just a1 in the numerator, over 1 minus r. All right, so we want to talk about some summation formulas, some common summation formulas that we talked about. The first one is the series the sequence 1, 2, 3, all the way up to n. So the sum of the first n terms, or the sum of n terms. So what we're looking at is a situation where we're adding up from k equal 1 to n. We're going to add up all of those terms. So that is going to be equal to however many terms you have times 1 less than the number of terms over 2. All right. Another one that we looked at was the sum of k squared terms. So 2 squared is 4, 3 squared is 9, all the way up to n squared, whatever n squared happens to be. And we proved that this summation is equal to n times n plus 1 times 2n plus 1 over 6. All right, so those are two of the most common. And what that allows you to do, we'll take a look at the proof for this in a second, but what that allows you to do is find the sum of something to the effect of this, a little bit easier too. K squared plus k plus 1 from k equal 1 to n. All right, so what we can do in doing that is we can break it up into 3 different summations and then just use those formulas. So we can look at the sum from k equal 1 to n of 2k squared. Well, we know the formula for k squared is this guy, so we just multiply that by 2. The formula for the sum of the first n terms, the summation formula for this is just n times n minus 1, so we can break that up into its own summation. And then this last one here, we know would just be the sum of 1 a bunch of times, so k equal 1 to n. So essentially what we can do is use these formulas in order to simplify a little bit one long summation into a couple easier pieces. All right, next thing we want to take a look at is mathematical induction. We'll tie this directly into what we just looked at, those summation formulas. So I'll go through a proof with you here in a second. Mathematical induction, there are 3 basic steps. Number 1 is we're going to look at the first case. So they're going to say prove something by mathematical induction. What you do is we're going to let n equal 1. So we're going to prove that it works, whatever it is, whatever the claim is, for the first case. So actually a lot of times this is just plugging in a 1 for n and then kind of grinding out some arithmetic and showing that you get an equivalent statement. All right, the next thing is assume that n equals k. So what we're doing in this step is picking an arbitrary value, or an arbitrary term, I should say. Arbitrary term. And writing an expression for that arbitrary term. Okay, so we show it works for the first one. Pick an arbitrary term in the series, and let n equal that arbitrary term. That's k. That's the arbitrary term. And then what we're going to do is show it works. So we're going to let n equal k plus 1. We're going to show it works. And by it, I mean whatever the argument is. Same thing up here. Show it works for the next term, for the term after that arbitrary term you picked up here. And in theory, what this means is when you pick an arbitrary term, let's say that arbitrary term is like the 80th term. If it works for the 81st term, and you can show that mathematically that it works for the 81st term, well, it doesn't matter then if this is the 80th term or the 140th term or the second term or whatever this arbitrary value is, it's going to work for everything. So that's how mathematical induction works. These are the 3 essential steps. These 2 steps are essentially just technical. You need to complete them, but they're relatively basic and straightforward. This step right here, this step 3 is the biggie. This is the one where you're actually going to manipulate. Can get a little bit nasty at times, and ultimately you want to use some sort of manipulation in order to show that your 2 statements are equivalent. So real fast, just want to give you an example of this. We did this in the notes earlier in the year. Using mathematical induction, prove that the sum from k equal 1 to n of k is equal to 1/2 n times n plus 1. And as I read that out loud, I just flipped back to this slide. This is n plus 1. So it's the term that we're on, the number of terms, and then one more than that number of terms. So make sure you fix that. Anyways, back to this. So we're going to go through these steps. So we need to show that when we add up this sequence of numbers to create a series, that it's equivalent to this expression right here. So we show that it works for the first one. Let n equal 1. Plug in a 1 wherever you see an n over here. Show that it works. Assume that n equals k, and what you need to do is you need to write this out. So here is the series. It's 1 plus 2 plus ... plus k, all the way up to k, and that's equivalent to this expression right here. And this is the key. This is what you're going to use in the next step. So once you write that series out as the expression that's given up above, we're going to use that in the next step. And the next step, let n equal k plus 1. So let's show that it works for the term after the arbitrary term that we picked up here. So write it out, write the series out, and then we're going to tack on the k plus 1 term, because that's how many we want. We know an expression for this. We defined it in the step before. So an expression for the sum of the first k terms is defined in the n equal k portion of this. And then from there, we just manipulate. All right, so we can factor out a k plus 1, and we're left with k over 2 plus 1, which ultimately we can manipulate into looking like what we want it to look like. The conclusion is another important part. Therefore, we want to show that the whole point of this was to show that it doesn't matter what term you're on. And so that's what this is saying. For all natural numbers, n, doesn't matter how many terms you're adding together, this formula is going to work. And so that's what our conclusion should say. Here's another quick example of a proof by mathematical induction. A little bit messier one, but I'm not going to spend any time going through this. I'll let you pause the video if you want to check that out. Check out all the work. Again, just the basic steps. Let n equal 1. Show that it works. Pick an arbitrary value. So assume that n equals the kth term, whatever that kth term might be, and write an expression. Write out the series. Okay, write an expression in terms of k, and then you're going to use that expression down here when you let n equal k plus 1, and then manipulate in order to make it work, and then there's your conclusion. So pause the video if you want to check that out a little bit more. Check out the math, but make sure you understand mathematical induction and the process. All right, guys, so the next thing we talked about was divisibility and the definition of divisibility. And this is the biggest part of this, because in any proof, in any divisibility proof that you do, you have to use the definition and show that the definition holds. So if A is divisible by B, then we know that A equals B times K, and you got to define what K is, okay? You have to define what K is. So in this case, K is an integer. So what all this is saying is that that A is a multiple of B, but this is how we define it. So in any proof that we do, we need to be able to show that this is the case. Whatever we're showing is divisible by this other thing, we need to show that it is a multiple, or you can take some integer and multiply it by that thing, and you're going to get that original argument. So that's generally what divisibility is. So a divisibility proof is prove. I'll do this real quick. N cubed minus n is divisible by six for all natural numbers n. So it's saying you take a natural number, then you cube that natural number, and then subtract the same thing, and it's divisible by 6. Well, we're going to prove this by mathematical induction. All right, so our first step is to let n equal 1. When n equals 1, we've got 1 cubed minus 1. That's equal to 0. So the question is 0 divided by 6? Well, in order to show this, that it's actually divisible by 6, we know that that k, when k equals 0, the situation then is that 0 equals 6 times 0. In other words, we've shown that 0 is equal to some multiple of 6 when k is 0. Therefore, 0 is divided by 6. So that's the first case. Next case you need to address or work on is we're going to assume that n equals k. So we're going to pick an arbitrary term here. When we assume that n equals k, then we've got k cubed minus k is divisible by 6. And what does that mean based on the definition? That means that k cubed minus k is equal to 6 times some integer, and we'll call it maybe I, just to change it up. And again, define anytime you're going to bring a variable into it. So for I in the integers. So next step, we've let n equal 1, showed that it worked. We assume that n equals k, and we're going to let n equal k plus 1. And we got to show that it works for the k plus 1 term. So what we're looking to do here is when n equals k plus 1, we just assume that it worked for the kth term. So now we're looking at k plus 1 cubed. We got to show that k plus 1 cubed minus k plus 1 is divisible by 6. In other words, k plus 1 cubed minus k plus 1 is equal to 6 times some integer. And it gets a little messy when you start bringing all these variables into it. But the point is, this one doesn't necessarily have to be the same as this one. All right? So we got to show that this expression is equal to 6 times some integer in order to show that this works for the k plus first term. All right, so we've got to do a little bit of manipulation. Let's take this guy and expand it. So we're going to get k cubed plus 3k squared plus 3k plus 1. Nice little application of binomial theorem there. You got your 1, 3, 3, 1. Minus k minus 1. We've got to show that that is equal to 6 times something, times some integer. It's a multiple of that. All right, and this, again, the key is that we're going to use what we wrote up here. All right, we're going to use what we wrote up here. So at some point, we're going to have to use this k cubed minus k in order to show that this works. All right, so here we've got our k cubed and our minus k, so let's go ahead and separate that. So that's k cubed minus k. And from above, again, from this assumption, we know that this is divisible by 6. So this is equal to 6 times some integer. So what's left is this guy's gone and that guy's gone. 3k squared plus 3k. And then this guy right here, we can factor, so we can take out a 3k times k plus 1. And ultimately what we need to do is show that k times k plus 1 is going to be even. And I say that because if it's going to be even, then it's equal to 3 times 2 times something. That's an even number. So we know that k times k plus 1 is going to be even because it's always going to be an even times an odd. And even times odd always equals an even. So we can rewrite this as 3 times 2 times something, whatever that something might be. And from there we know it's divisible by 6. Because we've got then 6 times some integer. So that's the general proof. You need to show that every component is divisible by 6, so it's equal to essentially show every component when you simplify, or expression, is equal to 6 times some integer in order to complete this proof. And then we would have a therefore statement, and it would just be a repeat of what we showed up top, or of what we were trying to prove up top. So this expression, therefore, this expression is divisible by 6 for all n in the integers. Talk about the binomial theorem very quickly, guys. the binomial theorem basically says if you have a binomial raised to an exponent, a particular exponent, then it's equal to this sum. And we talked a lot about the ties between this particular thing and Pascal's triangle. And so make sure that you understand that. But just again, real quick review. This is a combination. Statistics. In statistics, this means out of n objects, you are choosing k. In this particular setting, you can calculate this, and you do need to know how to calculate this by hand by using this formula. Okay, so we can figure out the number of different ways a particular combination can play out, or this is the number of different collections of something. And then this is going to be how we kind of figure out, we're going to multiply these two things together, and that would give you the remainder of your term. And that's really all I'm going to talk about. Most of the time we see things like 2x plus 1. Use the binomial theorem to expand that. So we would use this. It would be, in expanding this, the first term would be 3 choose 0, and then it's the first term, so that's 2x to the n minus k, so it's the third, times 1 to the k. We're going to add that to 3 choose 1, 2x squared times 1 to the first, plus 3 choose 2, 2x to the first, 1 squared, 3 choose 3, 2x to the 0, times 1 cubed. So we can expand this. You can find a particular term. Remember, this is the first term. This is the second term. So in terms of relative to term number, understand that this is going to be 3 choose t minus 1. So whatever term you're trying to find, the first term, it's going to be 3 choose 1 less than that term. This is going to be 3, the second term, you're going to look at 3 choose 1 less than that, so 3 choose 1, and so on. So that's generally how the binomial theorem works. Alright, so the next thing we want to look at is partial fraction decomposition. Remember, there are a couple things that you need to happen. Both of these things have to be present in order for you to use this method. Number one, the denominator has to be factorable so that we can actually split it into two different parts. And number two, it must be a proper fraction, meaning that the degree of the numerator is less than the degree of the denominator. Okay, we need both of these things to hold in order to do this. And so you need to check those conditions when you first do it. Number one, here's an example. So first example, I want to use partial fraction decomposition. Number one, is the denominator factorable? Yes, it is. Number two, is the degree of the numerator less than the degree of the denominator? Yes, it is. So both of those hold. So we can go ahead and break this apart. So what we want to do is we want to break it into its two most basic components, and then figure out what our constants are in the numerator. So this one, pretty easy one, x plus 2, x minus 2. So we know that 3 is going to be equal to a times x minus 2 plus b times x plus 2. From there, we're going to look at values of x. So when x is equal to 2, what happens? Well, when x is equal to 2, we get 0a, so we know that 3 is equal to 4b, and therefore we can solve for this coefficient. It would be 3/4. When x is equal to negative 2, we end up with b canceling, so we end up with 3 equals negative 4a, so a is equal to negative 3/4. So we should write our answer as an expression we're taking this and breaking it apart. So we end up with 3 over x squared minus 4 is equal to, a ended up being negative 3/4, so negative 3 over 4 times x plus 2. And b ended up being 3/4, so we're going to add 3 over 4 times x minus 2. Sorry, my program's kind of screwing up here. So this is your answer for this particular thing. Looking at an example where where a condition doesn't hold. Number one, this is factorable, the denominator, so that one checks out. But we don't have a case where the degree is less than the degree of the numerator is less than the degree of the denominator. So what we need to do first is long division in order to create that particular scenario. Okay, so we're going to take x squared plus 5x minus 13, and we're going to divide that by x squared plus x minus 12. We do this, we end up with 1, and we multiply this through x squared plus x minus 12. Subtract all of that. So these are gone. This gives me 4x, and that's a positive 12, so that's 4x minus 1. So what I turn this into is 1 plus 4x minus 1 over the same denominator I had before. And what that's given me is now the degree of my numerator is less than the degree of my denominator. And so I can go ahead and do partial fraction decomposition on this term right here. Just make sure that in the end, we're going to write our answer as, I'll let you go through that and try it. I'm not going to do it on this video, but our answer should look something to the effect of this. 1 plus whatever we break our this thing down into. So this would be something over x plus 4, x minus 3, and then you can go ahead again and figure out what your coefficients are. So our answer would look something like this. Alright guys, so last thing on this part 2 video is we want to look at the complex conjugate root theorem and building a polynomial, or building polynomials of least degree, and using this thing. So first of all, complex conjugate root theorem says that basically if the positive version is a root of a polynomial, then the negative version is going to be a root. So in this particular case, so if you look at the first root right here, what this basically means is that negative 3 plus 0 is a root, and negative 3 minus 0 is also going to be a root. Well, that's a little bit redundant for us, so we just stick with the 1. In this particular case, you get the positive version of this, so we need to include the negative version. So that means that our 3, it's actually got a third root, where 5 plus 7i is the root, is the expression for the root. Okay, so we want to build this function. So f of x is equal to some constant in front of this thing, just like when we built quadratics, although, but this is not a quadratic, this is a polynomial of least degree. And then use the factors. So x plus 3 is the first one, that's your first root. Second root would be x minus 5 minus 7i. So we would have to do a little simplification with that. And x minus 5 plus 7i. All right, so I'll let you guys go through that. We would plug this number in, go through, figure out what your coefficient is there, and then you can write that polynomial. But that's it for this video. Remember, this is not exhaustive. This does not cover everything that may be on the final, but just try to hit all of the major topics.